In the vast, shimmering ocean of space, just 4.24 light-years from Earth, lies Proxima B, a rocky world no larger than our own, quietly orbiting the red dwarf star Proxima Centauri. Although it is our closest known exoplanetary neighbor, reaching Proxima B with current spacecraft technology would still take tens of thousands of years. Thanks to the extraordinary capabilities of the James Webb Space Telescope, humanity has now captured the most detailed glimpse ever of this distant world, a potential candidate for habitability beyond our solar system. Proxima B was first discovered in 2016 using the radial velocity method, which detects subtle wobbles in a star's motion caused by the gravitational tug of an orbiting planet. These tiny shifts in Proxima Centauri's light spectrum revealed the presence of a planet orbiting remarkably close, completing a full revolution in just 11.2 Earth days. Estimated to be about 1.17 times the mass of Earth, Proxima B orbits roughly 20 times closer to its star than Earth does to the Sun. This close orbit likely means the planet is tidally locked, its dayside bathed in constant starlight, while its nightside remains locked in eternal darkness. Proxima Centauri itself is a red dwarf, a small, cool star known for its fierce volatility. Though far dimmer than our Sun, it frequently unleashes powerful stellar flares that flood its planets with intense ultraviolet and X-ray radiation. These violent outbursts threaten to strip away any atmosphere Proxima B might have, leaving its surface exposed and unprotected. Yet, despite this harsh environment, the possibility for life remains. It may hide in sheltered regions beneath the surface, deep within fractures, subsurface aquifers, or along the twilight boundary where temperatures could be moderate. On Earth, extremophiles thrive in seemingly inhospitable places like thermal vents, acidic pools, and radioactive caves, so it's not unreasonable to imagine life persisting in niches on Proxima B. Enter the James Webb Space Telescope, launched in late 2021. With its primary mirror composed of 18 golden hexagonal segments and operating near the second Lagrange point under cryogenic conditions, JWST is revolutionizing infrared astronomy. Its high-contrast imaging and coronagraphic techniques effectively block out the overwhelming glare of nearby stars, allowing astronomers to detect faint thermal emissions from planets like Proxima B. Once thought beyond reach, Proxima B is now within observational grasp. By precisely targeting Proxima Centauri and isolating the planet's subtle heat signature at specific infrared wavelengths, scientists have gathered data hinting at surface temperature variations, possible cloud formations, and preliminary clues about its atmosphere. The thermal map revealed temperature fluctuations across the planet's surface, cooler regions possibly indicating cloud cover or weather patterns, and warmer spots suggesting geographic diversity or thinner atmosphere. Most intriguingly, spectral fingerprints hinted at the presence of water vapor and molecules commonly associated with life's essential processes. Though these findings are not yet confirmed, they raise exciting possibilities about the potential for habitability on a world orbiting a star very different from our Sun. Still, Proxima B faces many challenges. Its close proximity to stellar flares and strong stellar winds means that without protective mechanisms, such as a powerful magnetic field, it could lose its atmosphere over time. If such a magnetic shield exists, it might protect pockets of habitability. Without it, the planet could be a barren, airless rock. Determining the true nature of what JWST observed remains a key challenge. Was the detected water vapor a real, lingering atmospheric feature or an observational artifact? Do the temperature differences indicate geological activity, or are they signs of climate and weather processes in action? To answer these questions, astronomers plan multiple follow-up observations using JWST, alongside complementary data from the upcoming Extremely Large Telescope and future space missions equipped with advanced starshade technology to block starlight more effectively. For centuries, humanity has wondered if life is unique to Earth. The discovery of Proxima B in our stellar backyard has transformed that question into a scientific hypothesis we can test. With JWST's ability to detect molecular signatures in distant atmospheres, we stand at a crucial turning point. Confirming water vapor, oxygen, or other biosignatures in future observations would mark our first solid step toward proving life beyond Earth exists. Proxima B will also help us understand atmospheres around red dwarf stars, which make up about 75% of all stars in the Milky Way. Understanding the climate, geology, and habitability of planets orbiting these stars opens the door to studying hundreds of billions of potentially habitable worlds. Habitable zones around red dwarfs differ significantly from those around Sun-like stars. Planets here may be tidally locked, exposed to intense radiation, and possess climates unlike anything in our solar system. Unraveling their evolution is key to assessing how common life might be in our galaxy. Technological innovation plays a major role in this pursuit. Conventional rockets would take over 70,000 years to reach Proxima B. But visionary projects like Breakthrough Starshot propose sending tiny, light-driven nanocrafts propelled by powerful lasers from Earth. If successful, these probes could reach the Alpha Centauri system, including Proxima B, within a couple of decades, capturing the first close-up images and environmental data from another star system. Though still in the concept phase, such missions have energized the scientific community and inspired international collaboration and funding. Meanwhile, ground-based observatories like the Extremely Large Telescope and the planned 30-meter telescope will offer increasingly powerful spectrographs capable of detecting molecular signatures in exoplanet atmospheres. Combining these ground and space-based data will paint a fuller picture of Proxima B's environment and potential for life. Our knowledge of exoplanets has exploded in the past 20 years. The Kepler mission identified thousands of planets by detecting transits, and TESS continues surveying the entire sky for short-period planets around bright stars. These missions revealed a diverse range of worlds, from gas giants to rocky super-Earths, lava planets, and ice giants in habitable zones. Yet Proxima B remains uniquely special. It is the only exoplanet close enough to allow detailed observations of climate dynamics and atmospheric properties. Capturing even hints of water vapor and possible weather patterns is a stunning achievement that expands our understanding of what may be possible around red dwarf stars. Detecting life will not be instantaneous. It may take years or decades of continuous observation, advanced calibration, and next-generation instruments. But progress is accelerating. Biosignature research is refining its criteria. Oxygen alone can be produced geologically. Methane might come from volcanic activity. However, combinations like simultaneous oxygen and methane far from chemical equilibrium are difficult to explain without biological processes. Further observations of isotopic ratios and cloud dynamics could help distinguish biological activity from geological or atmospheric phenomena. Proxima B reminds us that planets are dynamic, evolving systems, not static rocks. Their atmospheres respond to stellar radiation, volcanic activity, magnetic fields, climate cycles, and potentially, life itself. Every data point, temperature variation, molecular signature, surface reflectivity, adds a piece to this cosmic puzzle. We live in an era of unprecedented discovery. The ability to see another world in detail, study its climate, and search for life is no longer science fiction but near-term reality. For the Apollo missions, it was just one moon. For JWST, it is now one planet orbiting another star. One that could reveal whether life is rare or common in the universe. The implications for humanity are profound. Confirming life, past or present, on Proxima B would demonstrate that life emerges spontaneously under suitable conditions. This would fundamentally reshape biology, philosophy, and our cultural narrative. It would open new perspectives on biodiversity, evolution, and the resilience of life. It would confirm that Earth is not a lone cradle of biology, but part of a cosmic family of living worlds. Some argue that such confirmation could bring cultural shock, geopolitical tension, or technological risks. Others believe it will unite humanity, much like the Earthrise photo did, reminding us of our shared destiny. Regardless, the science presses onward. Each new mission, telescope, and observation gradually unveils a universe that is far richer and more complex than we ever imagined. As the James Webb Space Telescope continues to focus its infrared eyes on Proxima B and dozens of nearby exoplanets, humanity draws ever closer to answering the question that has echoed through the ages. Are we alone? Proxima B might already hold that answer. And with every new observation, we listen more intently, watch more closely, and dream more boldly about the worlds just beyond our cosmic doorstep.